Hi everyone, thanks for joining me today. So today, first we're going to go over what a network analyzer is, and then we'll talk about the transmission line and S-parameter theory. After that, we'll go over the block diagram of network analyzers and see what's going on inside them, and then we'll see what kind of measurements you can make with a network analyzer. Finally, we'll finish out with some talk about calibration and error correction. First, we need to make sure that we're all on the same page here. When I tell people I work with network analyzers, they're usually like, oh yeah, networks and internet and that kind of stuff. But back when network analyzers first came around, there were no computer networks and there was no concept of a wireless network. So when we say network and when we talk about network analyzers, we're referring to electrical networks, not the internet. So what is a network analyzer? It's an instrument that measures the network parameters of electrical networks. What this means is that we're measuring the effects of the electrical networks or components on a test signal. We send a known signal into a device, and we measure the signal after it comes out of the device, and that tells us how our device is interacting with the signal. We refer to measuring the network parameters of a device as characterizing the device. So why is it so important to characterize devices? That's because in RF systems, our goal is to get a signal from point A to point B as efficiently and cleanly as possible. Knowing the electrical properties of each component in your network helps you transmit a signal while minimizing the distortion on the signal. Here's a typical RF or microwave link with a transmitter and a receiver. The characteristics of the transmitter, like output power and operating frequency, and the characteristics of the receiver, like sensitivity and selectivity, dynamic range, these are all determined by the quality of the components that go into them. Network analyzers are used to test the individual components, like filters and mixers. And then once you've tested the building blocks of the system, you can put them all together and have a transmitter and a receiver that work very efficiently. We want to make sure that the individual components aren't generating distortion, harmonics, or anything else that will affect the signal. We also want to ensure a good match between the transmitter and the antenna so that we get good power transmission.
Early network analyzers were scalar, and they only measured the magnitude of a signal. But nowadays, pretty much every network analyzer is a vector network analyzer that captures both magnitude and phase. And this is very important for several reasons. First of all, having both magnitude and phase gives you the complete picture of your device's performance. And this is important to know for if you're designing matching circuits or if you're plugging these values into a simulation. It's also important for time domain characterization, vector error correction, and nonlinear or X-parameter characterization. All of these things go into giving you a full picture of your device's performance, and they come from having both magnitude and phase.
Now that we've seen how network analyzers fit into the RF world, let's look at the theory behind them. Let's start with some transmission line basics. At low frequencies, the wavelengths are much longer than the length of the wire or the length of the printed circuit board trace. The current travels very easily down the wire, and the voltage is basically constant across the entire wire. But as we move up into the RF and microwave frequencies, we find that the wavelength becomes equal to, or even much smaller than the length of the wire. And so this wire we call a transmission line. If we look at the voltage on a transmission line, we'll see that it actually varies due to impedance mismatches at the end of the line. So it's very important to match the impedance of the line to your device in order to get maximum power transmitted through the system. We call the impedance of the transmission line Z0. And so when we're connecting an element to the transmission line, like an amplifier or an antenna, we are trying to match to Z0. And so once you're matched to the characteristic impedance, then you'll have maximum power transfer. The value of Z0 in RF and microwave is typically either 50 or 75 ohms. And this value depends on whether your transmission line is optimized for low loss or for handling high power. So for example, a transmission line for cable TV is going to be optimized for low loss, while a cable for an antenna is going to be optimized for handling high power. Now let's look at what's going on between a transmission line and a DUT. RF energy actually travels pretty similarly to how light waves travel, and so we can use a lens analogy to describe this interaction. The term scattering actually comes from X-ray crystallography. They'll talk about having an incident signal reflected off of the device, and then there's a transmitted part of the signal. So with RF and microwave components, we actually use the same terminology. We talk about a power wave being incident on a device under test, and then we see how much power is reflected, how much power is transmitted. And here's some more terminology. In high-frequency device characterization, we refer to the incident wave as the A1 wave, the reflected wave as the B1 wave, and the transmitted wave as the B2 wave. So incident waves are A waves, and scattered, either transmitted or reflected waves, are B waves. And so then we can use these A and B wave ratios for transmission and reflection to get parameters like standing wave ratio, S parameters, reflection coefficient, gain, and a lot more.
Let's look at how the reflection parameters relate to the impedances we were just talking about. So we call the reflection coefficient gamma, and gamma is a complex number with a magnitude of gamma rho and a phase of gamma phi. And you can see it's directly related to the impedances. ZL is the impedance of the load, and Z naught is the impedance of the transmission line. And return loss comes from the magnitude of the reflection. And return loss is calculated as minus 20 log of the reflection coefficient. Now, since it's a loss, a positive number means it's lossy. But it's common to refer to a return loss as a negative number. So when people say a minus 20 decibel return loss, you understand that this means the same as a 20 decibel return loss. And conceptually, what this means is the reflected signal is 20 decibels below the incident signal. And finally is the voltage standing wave ratio. Two waves traveling in opposite directions along a transmission line will cause standing waves. The standing wave ratio is the ratio of the maximum to minimum voltage of the standing waves, and we can also determine that from the reflection coefficient. This visual helps illustrate how all of this fits together. So on the left side, if you have no reflection, then gamma is 0, and the voltage maximum and the voltage minimum on the line are constant. Your voltage standing wave ratio is 1. This is the ideal match case. Your load is perfectly matched to your transmission line and you're not losing any power. You can see the return loss is infinity, or colloquially, we would say the loss is minus infinity. When you see this value on a network analyzer, it'll usually be truncated to about minus 200 decibels. Of course, this is the ideal case, and in practice, we won't ever be able to reach a perfect standing wave ratio of 1. In the real world, a standing wave ratio of about 1.5 or lower is usually considered pretty good for most applications. And on the right side, if you have a very high reflection, the return loss will be 0 decibels and the standing wave ratio will trend to infinity. This is the case for a perfect short or a perfect open circuit. Now that we've gone over some of the theory, let's see how to actually characterize devices. For low-frequency devices, we like to use the H, Y, and Z parameters. These parameters depend on measurements of voltage and currents under various conditions, such as a short circuit or an open circuit. But it's hard to apply opens and shorts at RF and microwave frequencies, and sometimes you can even damage your components if you apply an open or short circuit. So we need a new way to do these at RF frequencies. And so in microwave and RF, we use scattering, or S parameters. And these are incident and transmitted waves that we consider to be terminated within the transmission lines. And there's a lot of advantages to them. They're pretty easy to obtain. You don't need opens and shorts, and they give you a lot of information. We can calculate gain, reflection coefficient, return loss, H, Y, and Z parameters, and more. We can also even cascade the S parameters of individual devices, and that'll help us predict the performance of an overall system. And finally, they're the most common tool to describe RF devices, and so when you're doing simulations and things like that, having the S parameters of your devices will be very helpful. And here's the setup for measuring S parameters. So for the forward S parameter at the top, we drive an incident signal into the forward direction and measure the transmitted and reflected signals. From there, we can calculate S11 and S21, and these are based on ratios of the reflected and incident waves, those A and B waves we talked about earlier. And then for the reverse S parameters, we do the same thing in reverse. We drive a signal in the reverse direction, and we come up with S22 and S12. The S parameters can be equated with common measurement names that we're already familiar with. So S11 is the input match, S22 is the output match, S21 is gain in the case of an amplifier, or we consider it loss if we're measuring a filter, and S21 is the reverse gain, also called the isolation. And it's important to remember that the S parameters, while we do express them in decibels, they're actually complex forms. They have both a magnitude and a phase. And so when you see them listed in decibel form, remember that there's also a phase associated with them, and this phase information is very important to have for things like simulations. So next up, I have a short video where I'm going to actually show you what the S parameters of a filter look like on a network analyzer.
This is a graphical representation of a couple of the S parameters of a bandpass filter. Now on this graph, we have frequency on the x-axis and magnitude of response on the y-axis. So as we sweep across frequency, we can see how our device responds to those frequencies. Now, as the name may suggest, a bandpass filter will only let a certain band of frequency pass through it. We can see this in the yellow S21 trace. Right there in the middle, there's only a small band of frequency that makes it through the device. So what's S21 actually telling us? S21 is measuring at port 2 what's coming from port 1. So we have our device connected to port 1 of the VNA. If we send a signal into it from port 1 and measure what comes through the device at port 2, that's our S21 parameter. S11, which is the blue trace on here, is measuring at port 1 what's coming from port 1. What that means is we're measuring the reflection that goes out of port 1, hits the device, and then comes.
And so since the S parameters are complex numbers, we can plot them on a Smith chart. And what the Smith chart does is it takes the real and imaginary impedances and turns it into a vector chart. So here on the top right, you can see on a polar plane, we can plot rho and phi. And if we plot the magnitude and phase of the reflection coefficient on this polar plot, it doesn't really tell us anything about the impedance. But on the Smith chart, we have circles of constant resistance and circles of constant reactance. So then we can plot vector, rho, and phase, and that will tell us the impedance of our device. So now that we've gone over a lot of the theory, let's look at the network analyzer block diagram and see how this all works. Here's a high-level network analyzer block diagram showing the key elements. We have a source for the RF signal, we have directional devices to separate incident and reflected signals, and we have receivers for measuring signals. And from this diagram, we can see that network analyzers make ratioed measurements. The reference receiver samples what's going into the DUT, and then the measurement receiver samples what's coming from the DUT. And so by comparing what's going into the DUT to what's coming from the DUT, we understand how the DUT's operating. Let's start by looking at the source. The source is the stimulus for your measurements, and they can typically sweep frequency or power. In more advanced network analyzers, you can also sweep phase. And network analyzers traditionally only had one source, but a lot of modern network analyzers have multiple sources. And this is useful for using the second source as a local oscillator for mixer measurements, conversion loss and group delay measurements, and you can also use both sources to create two tones for two-tone intermodulation distortion measurements. Next is the signal separation, and this separates the incident signal from the reflected signal. And there's a couple ways to do this. You can measure the incident signal through a power splitter, where part of the signal is sent to the reference receiver and part is sent to the test port. But the most common way to do this is with a directional coupler because that'll give you better isolation. In low frequency applications, you want to use a directional bridge because it provides better low frequency performance than a directional coupler would. One term you'll see a lot when you're looking at couplers is directivity. And the directivity is defined as a measure of how well a coupler can separate the incident and the reflected signals. And the typical way we look at directivity is we measure how much signal is reflected from a large reflection, like an open or a short, and we compare that to how much signal is reflected when you place a load on the same test port. You can also compute directivity from three measures of the directional coupler: the isolation in the reverse direction, the forward coupling, and the main arm loss, which are all pictured here. And directivity is important to consider because you can get some pretty significant errors if you don't account for it. So for example, if you have a situation where the return loss is very low, you might find that the return loss and the directivity are equal and opposite. They cancel each other out and you get an artificially low reading. Or you might find the directivity and the reflection are in phase and you get an artificially high reading. But most of the time you'll get some sort of error when their phase is random, and that'll just result in all of these fluctuations that you see here. And we can use vector error correction to get rid of most of the directivity error if our system is properly calibrated. Next, let's look at the receivers. You can see here that the receiver contains a down converter, an intermediate frequency or IF filter, and then an analog digital converter to digitize the signal and send it to the network analyzer's processors. The piece I want to talk about here is the IF filter. And what this filter determines is basically the chunk size of the data that you're taking in. And so if you have a narrow filter, you're taking in small chunks of data, and this will give you faster measurements, but it'll also decrease your accuracy. And so there's a trade-off you have to consider when you're setting your IF bandwidth. So here's a visual of what setting the IF bandwidth actually does. This graphic is from our spectrum analysis literature, but it's still a great illustration of the concept of what's going on. So the narrower your bandwidth, the more details you'll pick up. This improves your dynamic range and reduces your noise floor, but it also slows down your measurement because you're taking in so many more data points. So when you're choosing an IF bandwidth, you want to consider the trade-off between accuracy and speed and figure out what's ideal for your particular measurement. Another term you'll hear a lot when people talk about network analyzer receivers is dynamic range. And the dynamic range of a network analyzer is the range of power that the analyzer can measure without unwanted errors. So in other words, it's the difference between the maximum and the minimum power that the receivers can handle. And having a wide dynamic range is important because it gives you a buffer between the noise floor and the measurement. And this graph on the left shows you how the noise floor can affect your trace. For example, I have this filter on the right with 60 decibels of isolation. If I have 39 decibels between my signal and my noise floor, according to the graph on the left, this will cause 0.1 decibels of noise variation in my trace. So if I want to measure this 60 decibel filter with 0.1 decibels of accuracy, I need to set my dynamic range to 99 decibels. Now that we've talked about the basic parts of a network analyzer, I want to show you a block diagram of a more modern network analyzer. This is a 2-port PNA-X, and we can see the parts we've talked about. There's sources, receivers, and directional couplers, but there's also a lot of new circuitry here. We've got step attenuators, a low noise receiver for noise figure measurements, pulse generators and pulse modulators for pulsed S parameters, and two sources that can be combined to create a two-tone signal at the output. So the more advanced network analyzers go well beyond S parameters, and they can do things like intermodulation distortion measurements, noise figure measurements, and even spectrum analysis. This is just a 2-port model, but 4-port models are also very common these days. And if you need more than 4 ports, there's also PXI network analyzers available. Now these are interesting because they've completely redesigned the network analyzer to be able to fit as many ports into as small of a space as possible. And this is really important as modern antennas become more highly integrated. Like, for example, the front end of a phone can have 14 or more ports. And so we can fit 32 ports or more into a single network analyzer and have them all perform the same measurements with the same stimulus. Or you can configure it as a multi-site network analyzer, which means you have multiple independent network analyzers all on the same chassis. And that's really helpful if you want to increase your throughput. So for multi-port applications like high-speed digital cables and front-end modules, having this multi-port ability is very important. So now we know the theory and we know what's inside a network analyzer and what they look like. So let's start looking at the kind of measurements that you can make with a network analyzer. So at a high level, we have two kinds of devices, linear and nonlinear. And linear devices, as the name suggests, have a linear output with respect to their input. And nonlinear devices have a nonlinear output with respect to their input. And so the nonlinear behaviors, we typically see it as compression or clipping, and that can generate harmonics. But if your device has a nonlinear phase, a modulated signal can have some portions of the signal delayed differently than other portions of the signal. So then that will cause new kinds of errors in the modulated signal. So ideally, we'd like our devices to have linear delay and linear amplitude response, but unfortunately, that's not always the case, and sometimes you have to account for these nonlinear behaviors. One of the most important measurements to make for active devices like amplifiers is to find their gain compression point. And gain compression tells us where the amplifier transitions from the linear region to the nonlinear region. So an amplifier will reproduce the signal that's put into it up to a certain point. And once it can't output enough power, then the signal will just flatten out like we can see in the compression region. So when you're measuring gain compression, it's important that your source has enough power to reach the compression region of your DUT. And if your network analyzer source itself doesn't have enough power, you can always use an external power source to drive your DUT. Another cool thing you can do with a network analyzer is look at your devices in the time domain. So sometimes when you're looking at a transmission line or some sort of DUT in the frequency domain, you might have some poor return loss, but it's hard to tell what's causing it. But network analyzers can apply an inverse Fourier transform, and you can put that data into the time domain, and then it'll show up much more clearly. You can see in the graph on the right that anytime there's a bump or a kink in this cable, we can see it on the time domain graph. And this is very helpful for troubleshooting where bad reflection might be coming from, or if there's some other sort of fault in your system. This helps give you a visual representation of where it could be. Finally, let's talk about calibration and error correction. So why do we need to calibrate? Well, despite our best efforts, we still haven't made perfect hardware. And so whenever you're connecting your network analyzer to your DUT, you've got to use cables and fixtures and connectors, and there's slight defects in all of these, and no connection is truly perfect and repeatable. And so all of this will affect the accuracy of your measurement. And we can recover some of this accuracy using what we call vector error correction or vector calibration. Now, when I say calibration, this is different from the calibration where you send your instrument into a metrology lab every year. This is an error correction or a calibration that you can do in your own lab very regularly. And this calibration that you do yourself will remove the biggest contributor to measurement error, which is systematic error. And this will give you the best picture of your device under test. So when we talk about measurement errors, there's really three main categories of errors. There's systematic errors, random errors, and drift errors. And systematic errors are due to imperfections of the network analyzer and the test setup itself. And these are things like cable loss and cable mismatch. And this is usually the biggest source of error in any measurement. And then there's random errors. These are things like noise and connector repeatability. And there's not really much you can do about random errors, but you can reduce the effect of them through averaging. Finally, drift errors are things like the instrument or the cables drifting from their calibration due to a change in temperature or just over time. And the best way to get rid of these is also to recalibrate. And there's actually modules you can get nowadays that sit in your measurement setup, and with the push of a button, you can just immediately take it back to its calibration state. So that's pretty cool. So let's look at some of the systematic errors. Like we talked about earlier, we have directivity, where we see some signal in the test receiver that doesn't come from the device under test, but it actually comes from the directivity of the coupler. And there's also crosstalk, but in general, modern network analyzers don't really have any significant amount of crosstalk. It's usually hidden in the noise floor of the network analyzer and almost negligible for most applications. And then also, if we have a test port that's not perfectly matched to the Z0 impedance, you get some mismatch that can also cause ripple in the measurements. You can get mismatch from the test port or connected to the load. And so in total, we've got 6 forward and 6 reverse terms. So that's 12 error terms that we need to correct for. And the math for 12 error terms is a little deeper than we want to get today. We have literature where you can read about it if you would like. But for now, we're just going to talk about error correction at a high level. So let's look at a couple types of error correction. The simplest one is response or normalization. And what it does is it corrects for loss or tracking error of the system. And it's simple, it's fast, but it doesn't completely correct for everything. So if you want full error correction, you want vector error correction. And for this type of error correction, you need more calibration standards. You need a short, open, load, and through, or other types of standards depending on your type of calibration. And it'll account for all of your systematic errors, but it also takes longer to perform. And so one way to get around that is to use an electronic calibration kit where you only need to make a single connection, and then it'll electronically simulate all of the short, open, load connections that you need to make. And that makes the calibration process a lot faster, a lot easier, and it reduces the wear on your connectors. So what kind of calibration is right for you? Well, if you don't need too much accuracy, and say you're connecting directly to the test port of the network analyzer, you could just not perform a calibration and do an uncorrected measurement. And this is a convenient spot check just to get a rough idea of what's going on with your DUT. Generally won't be too accurate, but if you just need to make a quick measurement, it'll get the job done. Or if you have a cable, you can just perform a quick response calibration to remove the effect of the cable, and then you can also do a quick and dirty measurement with the cable. Now, if you want to make reflection measurements, you're going to at least need to do a one-port calibration, and that'll give you the most accurate error correction for reflection. If you're doing transmission, you're going to have to do a full 2-port calibration. And there's a few ways you can do that, but the end result will be the same, is that you'll have fully error-corrected 2-port measurements for both reflection and through measurements. And so when I talk about making short, open, load, through connections, these are known standards that you're using as your connections, and they come in a calibration kit. They're verified by a metrology lab, and it's the best way to get accurate measurements. And the number of standards you need depends on the type of calibration you're doing. So for example, if you're just doing a response calibration, you're basically normalizing your measurement to a known device. So you really only need a through connection for that. And then for 1-port calibration, you need an open, a short, and a load. And then the full 2-port calibration requires 10 measurements using these different pieces in different configurations between the 2 ports. Here's what calibration actually looks like to your network analyzer. On the left, before calibration, the network analyzer considers everything beyond its test ports to be the DUT. Obviously, this is a problem if you're using cables to connect your device, because the cables, the connection between the cable and your DUT, and any other fixtures are going to be factored into the measurement. And so then after you calibrate, on the right, the network analyzer moves its plane of reference up right to the DUT, and it's able to tell itself, okay, I can ignore the cables, I can ignore the connectors, I now know where the DUT is. And so coming up next, I'm going to show you some traces before and after calibration and show you how significant calibration can be.
Here we have a poorly calibrated trace. A few things could cause this. Maybe the temperature in the room has changed after calibration, the cables and connectors have been swapped out, or it's just been a long time since the last calibration. So as you can see, the noise floor is extremely noisy, and even in the passband of this filter, there's some strange reflections. So let's calibrate this and see how it looks afterwards. Now here's the same filter with the same stimulus after calibration. We can see the noise floor is a little lower and the reflections in the passband are gone. This is now a measurement that we can rely on.
All right, now we've gotten through a lot of theory today, and so as a bonus topic, I want to switch gears a little bit and talk about network analyzers in the real world. And so I just want to talk about more tangible topics and ways that you can apply this knowledge to your own labs. First, I want to address some network analyzer myths. And so myth number one is that network analyzers are hard to use. And you'll either hear this from colleagues or you'll think it yourself. You're looking at these instruments, there's all these buttons, there's all these cables and jumpers, and it can look pretty daunting at first. And so this is probably one of the most widespread myths about network analyzers that I see. The truth is network analyzers are actually incredibly user-friendly. They all have very modern UIs. A lot of them have a touch screen, so you don't even have to think about which button to use. And there's also plenty of measurement wizards built into the network analyzer that help you set up your measurements. There's tutorials and guides and help online. And so if you really want to start using a network analyzer or get better at using one, there's plenty of resources available, and it's definitely not that hard of a task. When you're connecting an RF cable like the one you see here, there's a nut at the end of it that you have to screw on to the connector on the other device. And so one thing you may hear in the lab is, oh yeah, if you get it as tight as your fingers can turn it, then that's about 0.8 Newton meters. And that's just not the case. And so while hand tightening can be adequate for a quick and dirty spot check, if you really want measurements that you can rely on, you're going to have to use a torque wrench. And torque wrenches come in different strengths depending on the type of connector you're using. So make sure that you're getting an adequate connector contact by using the right torque wrench for your application. And the final misconception I want to clear is that network analyzers are just unaffordable. A lot of people think it would be great to have one, be able to make all kinds of measurements, but it's just not feasible for them. And we'll talk about why that's not the case. There's so many different kinds of network analyzers out there that there's something that's optimized for any budget and any measurement need, from portable models to benchtop models to PXI models. There's really something for everybody. And if buying isn't right for you, there's also plenty of rental options also. So before giving up on a network analyzer, definitely explore your options and see what'll work for you. So now that we've finished going over the fundamentals, and I'm sure you're all real excited to go impress your friends and family with your new knowledge, I want to point out a few pieces of literature that I'm linking to from this webinar, and I really encourage you to check them out and continue your education. And the first one is a web page, and it actually follows a really similar format to this presentation. It goes over the basics, it goes over the hardware, and it goes over calibration and some of the measurements you can make. And this is a great coffee table level reference for you to check out, and it links to more advanced content if you want to dig a little deeper, and it's a great high level, easy to read, casual resource. And the second piece of content is this application note, Understanding the Fundamental Principles of Vector Network Analysis. And it's perfect for if you want to dig a little deeper into the theory. It goes over wave equations, it goes over transmission lines, it goes over the Smith chart. And so if you want to really look at the math and understand what's really going on behind all these network measurements, then this application note is a great resource to get started on that. And then the last piece is understanding and improving network analyzer dynamic range. And this is a great piece for going a little deeper into the math behind dynamic range, the noise floor, and then it also goes in depth about ways you can improve your dynamic range. It talks about the pros and cons of averaging, changing your intermediate frequency bandwidth, and things like that. And this is a great resource for getting to the next level of understanding of dynamic range because it's one of the most important topics when it comes to network analyzers and making measurements. And finally, if you really want to go to the next level, those of you who are familiar with this webcast series will remember Joel Dunsmore. He has forgotten more about network analyzers than I know, and he's got a lot of knowledge, and he put a lot of it into this book here, the Handbook of Microwave Component Measurements. And it has all the theory, all the math, all the advanced measurements that you could ever hope for. So if you really want to understand network analysis, this is, in my opinion, one of the best resources out there for that next level of knowledge. And that's all I have, so thank you so much for joining us today. I really appreciate you coming here, and I hope that this was educational, interesting, and informative. And so I'll turn it back over to Eileen now, and she'll take care of some housekeeping, and we'll get into the Q&A.
Thank you, everyone. Before we begin the Q&A session, I would like to call your attention to the survey questions we'd like you to take the time to answer. If that window is not showing on your console, click the icon in the widget bar at the bottom of your screen. The survey questions are, how would you rate the overall technical content of this webinar? After viewing this webinar, do you have a need for any of the following solutions? If you have a solution need, what would your time frame be? Also, we'd like to understand what your key business challenges are, and if you have any additional comments or suggestions for future topics. Now it's time for our question and answer session. If you would like to ask a question, please click on the Q&A icon at the bottom of your console. We'll try to answer these during the webinar, but if a fuller answer is needed, or if we run out of time, it will be answered later via email. Please know that we do capture all of your questions. So Matt, let's get started. Our first question that's come in is, how often do I need to calibrate?
Sure. So as far as how often you need to calibrate, generally anytime you replace a test cable, change a connection other than your connection to the DUT, or increase your frequency range or the number of points that you're measuring, you need to calibrate again for those new conditions. But if you're not changing any of those, we recommend calibrating daily, or at the very least, verifying your calibration daily. And the way to make your calibration last as long as possible is if you are able to maintain a stable temperature in your test environment within about 3 degrees Celsius of when you calibrated, and also using high quality cables and connectors will help your calibration stay valid longer.
Okay, thanks, Matt. Here's another question. How high in frequency can a VNA measure?
Out of the box, high-end ones can usually go up to 67 gigahertz, but with external frequency extenders, you can go as far as a few terahertz with some of the custom solutions, so really as high as you need them to measure.
Okay, thanks, Matt. Here's another one. How can I reduce noise in my measurements?
There's a few ways to do this. The easiest one is just to increase the power of your measurement. And what that'll do is it'll boost your signal away from the noise floor. And as long as your power isn't so high that you're getting compression in your receivers, that'll be the fastest and easiest way to do it. You can also reduce your IF bandwidth. That'll give you better resolution in your measurements, which will reduce the noise, but it'll also make the measurement take longer. And then finally, when all else fails, you can always use the averaging feature, and that'll get rid of random noise.
Excellent, thank you. And here's a question related to the spectrum analyzer functionality on the Vector Network Analyzer. Is it as good as a regular standalone spectrum analyzer?
That's an interesting question. As far as performance, yes. The VNA has excellent hardware, and it makes it a fast and accurate spectrum analyzer. It's really good for finding spurs and general debugging. However, if you want to do things like pre-compliance testing or any of those other specialized applications, you're going to need a standalone spectrum analyzer for things like that.
Okay, thanks, Matt. Great answer. And here's one more question. Is it possible to be able to make measurements on either a wafer or a PC board?
Absolutely. A lot of devices don't have connectors these days, so there's all kinds of fixtures and probes you can use to measure devices on wafers and PCBs. You will have to de-embed these fixtures from your measurements, or you can just use an automatic fixture removal software that does it for you. And so you'll be able to get the same quality of measurements on a wafer or a PCB as you would on a connectorized device.
Okay, great. So it looks like that's all the time we have today for Q&A. Thank you all for your participation. And we will respond to your questions via email, the ones that we didn't get to. This concludes today's webinar. As a reminder, you will receive an email when the recording becomes available. Download the slides now in the Resources widget. For more webinars in the series or to view upcoming events hosted by Keysight, you can go to www.keysight.com/find/events. Thank you again for attending today's webinar, brought to you by Keysight Technologies, and join us next month for the continuation of our engineering education webinar series. And enjoy your day or evening. Thank you.